Okay, why don't we get started? So I'm Mike Douglas, and this is the last topical week of our mathematics and machine learning program at the CMSA. And we'll be discussing rigorous numerical methods, partial differential equations, and related topics with Javier Gomez-Serrano and Tristan Buckmaster, and many people who will shortly introduce themselves. Finally, we'll go around the room. Everybody will make introductions and say something about both themselves and what they hope to get out of this week. And then it's very open-ended, but we'll try to decide together what topics to focus on this week. We may have focus problems, we may have other focus questions. So I'll start. I'm Mike Douglas. I'm trained as a theoretical physicist, worked in a wide variety of things, and I'm mostly focusing on applying AI and its applications to math and science very broadly.
Hi everyone, I'm Freddy from Queen Mary University of London, and I work with machine learning in the context of string theory, and so I'm interested in differential equations in that they appear a lot in string theory and theoretical physics in general to specify the dynamics.
Hi, I'm Tomás Silva from University of Campinas in Brazil. I'm a computer engineering by training, but now I'm doing my PhD in geometry. So more recently, I've been more interested in more algebraic geometry stuff, but I spend a lot of time studying flows of geometric structures of certain manifolds that involves a lot of PDEs. So I think this week will be very exciting, at least for me.
Okay, I'm Thomas. I'm a postdoc at MIT. I'm also mostly working in string theory and in geometry, problems of geometry related to that. I'm applying machine learning methods to both of those. In particular for PDEs, I've done a lot of work on solving PDEs numerically with machine learning methods on Calabrian manifolds and other geometric structures related to those.
Hi, I'm Adam. I'm a mathematician. I don't know anything about PDEs or numerical methods, but I'm very happy to learn, and if there's any problems, I would like to try to contribute.
I'm Maria. I'm a PhD student at Brown, and I'm interested in machine learning PDEs and computer-assisted proofs.
I'm Chris. I'm a PhD student at Oxford doing string theory, numerical geometry, and such things. So I'm also interested in, have done some work in this area.
I'm Ashin. I'm a PhD student at Cambridge. I have a sort of similar research interest to some of the people so far, string geometry and PDEs or manifolds. And I think I'm really interested in learning more about proper sort of existing numerical PDE methods, because I feel like I've learned more kind of machine learning techniques without sort of bypassing all the traditional stuff as well.
So my name is Amar Hayat. I'm a professor at École des Ponts in Paris. I work mostly on control of nonlinear PDEs, and on the other side, that's predicting mathematical quantities with neural networks or automated theorem proving. So I'm very interested that there's a week that seems to be linking both of them. And
Hi, I'm Sébastien. I work in Google DeepMind. I'm interested. I've been doing quite a lot of physics recently, theoretical physics, lattice-QCD, and generally I'm interested actually in all application of machine learning to maths and science. I like to dabble in different fields.
Hi, I'm sorry, Jordi. I'm Jim Halverson. I'm a physicist by training. Work on lots of different things. I'm really excited about this Calabrian work that people have been doing, and I wrote a paper recently with Fabian about how that relates to Ricci flow and sort of ML theory perspectives on that.
I'm Georgi. I'm from New Hampshire. I'm also studies applications of machine learning techniques to string theory, and in particular, like applying solving certain kind of PDEs on Calabrian manifolds. And I guess I'm hoping to understand how numerical techniques for neural networks for solving PDEs can be used to prove some rigorous results.
Hi, I'm Fabian Ruder. I'm at Northeastern University. As most other people, I'm also sort of interested in PDEs that come out of string theory. With Mike, separately, actually, we have some code that calculated or that approximated Calabrian metrics by solving some PDEs as strings that we also used it in the opposite direction. So try to learn about Ricci flows from the more theoretical computer science side, and I would be interested in how to get more quantitative, or how to sort of quantify the errors better of the PDEs we're solving.
Hi, so I'm Tristan Bagmas at NYU. So I work in fluids, so fluid equation. And so, I mean, I'm interested in how the main thing is proving to blow up for fluids. And so we use, I mean, there's two aspects of it, which is the one is using machine learning to find exact solutions to PD, which correspond to in this case, the self-same relations. And the other aspect is interval arithmetic, is how do you take something which is sort of like a numerical solution and transfer that into rigorous bounds that you can actually use in proof.
Yes, I'm Javi Gomez Serrano. I'm based at Brown, and as Tristan said, I'm interested in PDE, broadly in PDE from fluid mechanics, and this interaction with more computer stuff, lately AI, but also rigorous numerics and computer-assisted proofs.
Okay, thanks. Drew, you're
I'm a computational number theorist at MIT, so I generally don't work with PDEs a lot, but I do have an interest in dynamical systems. But I'm generally interested in applying machine learning methods to mathematics quite broadly, so I'd be very curious to hear about some of the ideas that you're going to be pursuing this week, and yeah, hope to learn more.
great, thanks. Okay. So let's see. I mean, it's very open. I mean, I'm not quite sure how to organize it. In many of the previous weeks, we kind of either had data or we had problems. You know, kind of this big source of problems, and we made a list of problems up on the board and split up into smaller groups to work on those problems. So that's one mode of operation. Last week on theorem proving, we did not do that. There were many people wanting more of an introduction into lean and the theorem proving and the use of AI to help with theorem proving. And so we had tutorial lectures and much more organized like that. It is a field where there is this very developed technology, both the mathematical methods of PDE, which speaking for many of the physicists here, we at least know they exist, but we would like to know more than that. And then the computer implementation of these. And so we could think of it as much a part of it as being a tutorial on these methods. Of course, there are many related problems that we could get our hands dirty and try to work on. So it's really very open. Another thing which we did in some of the previous weeks was to have talks about software and databases which were new or which few of the participants knew about, and so to kind of spread the word to get a tutorial on how to use a particular piece of software or whatever. So these are all possibilities for us, or we can be more open-ended. So I'll turn it over to you guys to either which of these things should we explore first? Or...
I mean, I came up with a couple of problems, but I don't know, depending on the background and the interest of the people, I don't know.
Okay.
Whether they will resonate or not.
You can propose some,
but we can try.
See what we think about them. That's right.
Yeah, I mean, there is this disclaimer that none of these problems can be solved in 1 week, so don't have to expect that. So I think these are doable problems. So I'm not going to.
I guess the one behind you is
this one
is more visible.
Okay.
Switch.
Sorry.
You can also connect to Zoom maybe.
That's right. If you want to connect your back to Zoom and share.
No, I think I'm fine as it is, and I'll just write on the board.
We
I mean,
like
really,
to
this
like the right
depends.
side of the board more.
This one? Or more
No,
like
actually,
that?
that,
Oh,
yeah,
this
the left side seems to be actually, it's a wide angle camera. Yeah, maybe the middle.
Yes.
That's right, don't go.
Yeah.
Yeah, right, good. Okay, good.
Okay, good. So I'm going to skip a lot of details, but just to give kind of a flavor of the type of problems that maybe one can try. So feel free to like. The background of everyone looks very heterogeneous, so feel free to stop me. Okay, so these are, well, the first one is coming from fluid mechanics. So this is the stability. Is the font big? Of something called the Lamosin vortex. And essentially, so again, I'm going to skip a lot of stuff. So this concerns, okay, so this concerns, so this is related to solutions of 3D incompressible Euler. Under stability.
You said that the Lamosin vortex?
Yes. And you'll see in a minute why it's called like that. So let me take this background flow, U to be V, the direction is theta. So here R is, I'm in 3D, but I'm going to be only looking at things that are planar. So E theta is 160 over R. Okay, and then I'm going to linearize 3D Euler around U bar. Okay. So there is a lot of, let's say, wishful thinking here, but believe me, through the calculations, okay, so after some calculations, and I'm going to define big omega to be V over R. I didn't tell you yet what is V, but I'll do so in a minute. And big B to be this quantity here. Then we're going to get some system of equations. Let me write maybe not the whole thing, but just to give a feeling of how this looks like. Now everything is only up. Well, in principle, a function of R and D. And it's a linear problem. So there are two more equations, but let's not overload the notation here.
When you write IM, is that,
M is an integer, I is the imaginary unit.
okay. So the function is complex.
Yes. So now the question is,
And big V can be complex or big V?
I'll tell you in a minute what is big V. So let big V to be 1 minus V to minus R squared over R. This is the Lamosin vortex. And then the question is, so now let me write this thing as dt something, so u, v, w, etc. equals L for the other quantities. L here is a linear operator. So is the spectrum and the discrete spectrum of L stable. So in other words, there does not exist a lambda such that U of RT, V of RT, the dot equals U of R the dot E to the lambda T, and the real part of lambda is strictly positive. Okay. So, so one question. I mean, this is an open question, and there are some numerical results. But from the point of view, let's say, of machine learning, maybe try to look at this linearized operator, which is like bad, non-self-adjoint, etc., and try to understand the spectrum of it. So that would be sort of a subdivision of this task. I mean, first, maybe try to understand this thing from a machine learning point of view, and second, after that, like, do an actual proof.
Is it like a numerically stable thing? If we just do some nice discretization, will things just start blowing up? And so the challenge is that.
I believe, I mean, I haven't tried myself, but my feeling is that this is probably not as easy as one may think.
Yeah.
But
so this is not like a highly studied problem. This is relative.
I think some people have worked on it, and this is why I believe that it's maybe not trivial.
Yeah.
So that this question essentially kind of have like two parts, no? Depending on how deep we want to go, whether we're happy with, let's say, some numerical computation, and in general. So this is a motivation for understanding the operator, the spectrum of non-self-adjoint operators. So this is the general framework where, and this is, let's say, a concrete example of a concrete problem where maybe one can say something and even perhaps turn it into a proof.
And we have to treat the equation in 3 dimensions. It's important.
Yeah.
Okay. Have you?
I mean, three. Well, the overall thing is in 3D, but the functions, if we are already at this stage, they are functions of 2D.
I mean, the sources are 2, but then there might be some simple argument that if there's an instability, you can already see it.
Yeah, but the conjecture is that there is no instability. So that would be sort of easier if the answer was.
Well, still, I mean, there could be some argument that says that any instability could be exhibited in 2 dimensions, you know, and imposing this the symmetry. Is there such an argument or no?
Not that I think, not that I know of. But so the conjecture answer is that yes.
Okay. Well, that's already, you know, again, it's much easier in the computer to find a solution than to show that there's not a solution.
Right. Yeah. This is what I mean. That it's much harder to show that every eigenvalue is on the left half plane than to show that there is one on the right.
Yeah.
So this also makes.
Yeah, we can make this long list actually of problems that's only coming out of the string theory and all the rest of how do we show that X doesn't exist numerically. I mean, that's.
Okay. Yeah. No, we can sort of split this up even in more parts. I'm just only pointing out like some concrete motivation.
So we can put things on the Euler, and so you can put like a reference.
Yeah.
These equations, and then if somebody were to find a growing solution, that would be surprising, but that would be a very direct answer to your question.
Yeah, absolutely.
If nobody finds it, then we still have to wonder what that means.
No, this is, I mean, I don't know, probably 50, 60-year-old problem.
Okay.
At the risk of asking the obvious, M is the vortex number?
M is related to some Fourier mode on some direction. I don't know if that answers your question.
So in physics, we normally have some winding number associated with the vortex, and so every vortex solution is labeled by an integer.
No. Here M
Oh, I thought you said it was an integer.
M is an integer, but and maybe it has some topological meaning to that.
Yeah.
But this is coming from doing a Fourier transform and then looking at the nth mode in. Okay, I don't know exactly which direction now it is anymore, but
you know what the favorite thing that all string theorists do, and it's going to sound crazy to you, is to find the supersymmetric version of that.
okay.
There's a lot of the equations we're interested in. We have vortex equations, we have all this kind of stuff, and then there's some. Generally, you have to kind of modify and add a little bit, you know, like you might even add another field or something. But then you get this equation which is very much nicer, you know, just as, you know, in favorable cases, it's even kind of integrable, or at the very least, it's just much easier equation to study. And then the equation you're interested in isn't that, but there can be some perturbation that relates, you know, something that relates to things. So have you thought, not necessarily supersymmetry, but just some kind of.
No. I mean, I haven't really worked on this question myself. I know it's out there, and I thought it's maybe doable, or maybe one can learn something from this equation, but I haven't worked on the equation. On the question myself.
I mean, it's not a numerical idea what I'm saying, but it's certainly.
Sorry. Yeah. I'll put references on the Zulip as well, with more detail. I mean, this comes like a bit out of the blue, but I'll post
what
on
would be your first step if you really wanted to, as a student, first seriously look at this problem? Just
maybe
digitize it and start looking for stuff.
Yeah, maybe try to use machine learning to look at the spectrum to find the eigenvalues of these operators, something like that. I mean, it's a linear problem, so I don't know. Usually,
you just start with a random thing and evolve it and see if it grows, right?
But you could find part of the discrete spectrum, so that could be like that. That's a plausible thing that you could actually search for like look for eigenfunction pairs.
You could evolve it, but you could even discard the time dependent part. Look at this operator.
Yeah, for sure. But I'm just saying in terms of what's the no-brainer thing to do.
Oh, yeah, then you can just evolve it. It will probably go to
start
0.
With some random stuff and then it starts to grow, right?
Oh, yeah, you could do from a traditional numerical way.
Yeah.
You could exactly do that.
Yeah. That would be maybe the 0th thing to attempt.
That's a thing we probably could accomplish this week.
Yeah.
So do you know whether it's diff or something?
I don't know. Yes.
I was about to ask whether you think there's even a spectral gap or not.
Probably.
Yeah.
So this is why there is hope of making it into a group.
Okay, so it should be slightly easier than the.
Yes. So okay. Now let me ask a question for you. Maybe there is a Lyapunov function. Yeah. Why not?
What we did was working for finite dimensional systems.
Still, but let's project onto, I don't know, a big number of modes or even a small number of modes. Maybe that could be.
Then maybe, yes. I mean, the way we were doing it could probably work also for PDs. The only thing that was that what we're doing is saying, okay, we don't know the answer for a given system, so it's hard to create a trained data set. But then we do the other way around. We start from Lyapunov function. We create many possible Lyapunov functions, create many associated systems, and we try to learn on this. To be able to treat with cases where indeed, as you say, we're not either set or joined, superjoined, so it's complicated to say something.
I should say the general strategy that we have in all our work is that you start from an infinite dimensional system and you reduce to finite dimensions. And then you have to, because otherwise you can't do anything. But once you, like if you were to tackle this problem, in the end you have to do some reduction to finite dimensions, and then you study the finite. And then you have to show that there's an additional step, and you have to show that this reduction from infinite dimension to finite dimension, you haven't really lost it.
But usually there is a spectral gap, and with enough effort, usually.
Exactly, because there's a spectral.
So what kind of reductions do you use?
Just to project onto some basis, finite
basis. It could be position space or Fourier space or something.
No, then this is problem dependent.
You have to choose, depending on the problem, you have to choose a basis which is and you have to well design that basis.
And do you have any immediate idea for this problem?
I mean, I don't know. You decide sort of these things after looking to a bunch of pictures.
Okay, I mean, maybe that's a
As in,
skill or
it's-
art that we could learn. from.
Yeah, there's a skill in choosing a basis because you want to choose the basis in such a way that the projection is harmless, which is not
Right.
an easy
For sure, yeah, okay. I
choice.
mean, there might be something for us to learn from that.
Yeah, I mean, usually you would like that, like in your basis. I mean, this would be the dream, no? That in your basis, this operator is diagonal or has some structure or is close to that. And okay, depending on the choice of the basis that you pick, you may end up with a better or a worse matrix for that matter. So,
Okay.
so that's.
And normally the obvious thing is not quite correct. Like it may give you a good start,
Right.
but you have to design.
Yeah,
The
yeah.
basis
Well,
for
yeah,
that.
as physicists, we have some appreciation of this in our problems, but most of us haven't thought about this problem. For this kind of fluid mechanics at all, apparently. But okay, this is good. Do people want to keep discussing it, or should we?
Maybe let's use another word and just write like number 1 Lambosine because I'm going to erase it and just to keep going.
Why this V of R?
Why that is V of R is the base solution. So you're understanding the.
Why this particular choice is what I meant.
Oh, because of there are other choices for other vortices and so on, but this is sort of the one that Lambosine came with. And
Is
this
it
the,
more interesting than the other ones, or is it?
Yeah.
Okay.
Yeah. I think this is an interesting case and a nice case where people don't, which is like basic in some sense, but people yet don't understand its stability yet.
Okay.
So it also has some kind of pedigree, like as an old problem as well.
And what about just like a case where V is 1 over R itself?
That's not going to work. You're going to, because at the origin, I mean, you can cut it and take something which is 1 over R on the tails and R
I got it.
at 0.
Yeah.
I think that one is understood. But this one with the, which is more or less this one, no? Because if you expand, this is like R at 0 and 1 over R at infinity.
Yeah.
So I think that one, I have to check. But I think for that one there are results. But when you do the exponential thing, which it shouldn't be too much different from that one, then this is still okay. Thanks. And and I will post the relevant references on Zoom. Okay.
Okay.
So that's
one.
That's one.
So remember, but the other derivatives, so this was only derivative with respect to t, no other derivatives?
There are other derivatives, yes. Yeah. I put a prime somewhere, so that's a derivative with respect to t. Yeah, so but not too many. There are already, if you're concerned about having too many derivatives, there is only one, at most one, derivative with respect to one on the operator.
And it's not local.
No, everything is local. So I mean, it's a non-SOV, let's say, or a non-S system of ODs. Okay, so problem 2. I mean, there is a lot of kind of personal deformation here with the choice of the problem. So there is this something called Gratz conjecture, which is related to plasma physics. And here, depending on, I mean, it's good and bad because depending on who you are, people don't agree whether the answer should be yes or no. So that's scary, let's say. So it is, again, relatively easy to state. So let me take some domain in R3 and vector field B. From R3 to R3, B is the magnetic field. And now I'm going to look at the steady problem. So for MHC. So B cross curl B plus the gradient of the pressure. So P is scalar. Divergence of B 0. So in omega. And the B of N boundary of omega. And the question here is suppose that I have a non-trivial solution to this. Must omega be a torus, like a regular torus.
A solid torus.
Yes.
So there is a solution on the first solid torus.
Yes.
So are there other solutions, but other omegas?
That's quite
Correct.
a strong statement.
Yes.
Okay.
Yes, but even then, people disagree whether. Yeah, that's the point. I mean, okay, so there is an additional hypothesis, is that topologically the field, you have to assume a little more. Let me not write it there because then I will have to write a lot. It will be in the references, but let's keep the statement kind of simple. But yeah, it is that strong. It is as if you have like a very strong sense of rigidity embedded into this problem. Okay.
And
This is MAC.
and you can probably write down the solution on the torus.
Yeah.
Do you need any assumption on P?
Smooth.
And that's enough to assume it's a torus.
Yes. Yeah. And then, okay, so you can further simplify this. So if you assume that everything is axisymmetric, then one can write this instead of having to write it in terms of B, which is a vector field. I can write it in terms of a scalar field. I won't write the equation itself, but this is known as the Grad-Chapman equation. And again, I will work all of this.
So when you say torus, you mean it's a topological torus?
No, an honest torus, regular torus.
Yes, like a donut.
Like a donut, exactly. Yeah.
So if you find a different torus,
You're done.
torus, that's equally interesting for you.
Yeah,
Just to define a
absolutely.
torus.
No, this is actually, it has very, it has strong relevance to the real world, because this is what they use to model tokamaks. So if you can find a configuration for which this happens, then you're not in trouble when it comes to building tokamaks. Yes.
It's probably a stupid question, but what if P is equal to 0? Does the problem become obvious?
No, but then you have 4 equations and 3 unknowns. Yeah. So you may not have.
Okay.
You may only have the solution.
So it's an empty torus.
Yeah.
Have people tried to see in 2D what's going on?
Yes. In 2D, I don't think you. Then the answer is yes. I think so. I have to check, but I think in 2D you don't have enough potential flexibility. So even in numerical, there are a bunch of people who have managed to find some kind of counterexamples, but they cheat in some way because they either don't assume these topological conditions on omega, or they take omegas that are unbounded, for example, things like that. So you can construct a bunch of these things that are not tori, but you're violating some of the hypotheses that I didn't write. Okay, so far, another direction that this is all for. I mean, I'm assuming that everything is like smooth. Let's say C infinity function. If you allow for discontinuities, and then okay, there is a series of papers that construct counterexamples allowing for discontinuity. So, for example, for B, taking B's that are piecewise smooth, for example, with potential jumps on the B of a certain level of regularity. I forgot if they are C0 alpha, or like if they are piecewise with C0 jumps or C1 jumps. I don't remember, but things like that people have managed to construct. So it isn't clear if by imposing the extra smoothness, these things will sort of disappear or not. So even at the numerical level, nobody has seen such an example. So potentially one could use machine learning to construct these things. I mean, this is not easy because you're solving for omega and b. So I don't know how to do it.
So you said the community is split on that one?
Yes.
What would be an argument to believe?
Faith.
But yeah, there's kind of a lot of these things, like often they're believed to be like it's believed that it's the only thing just because no one's ever found it.
Yeah.
And then
You found one solution.
and for many of these kind of problems, just out of the blue, someone comes up with this.
Yeah, I'm going to comment on that. There is a follow-up to this question, which is exactly that story.
Yeah.
So this is, and this, you can do some identifications between B and U, and this B and another B, and you can transform this steady MAC into some steady Euler equation, 3D incompressible 3D Euler equation. So now, to the point of Tristan's story, there are constructions in the axisymmetric, in the toroidal case, so for 3D Euler, so Gavrilov, this is 2019, constructed solutions where B is convexly supported on tori. So the point is not just that there is one silly trivial solution, but in fact there are many. Okay, and this was completely unexpected. Before 2019, people believed that there were no such.
It's conjecture to be false.
Well, yeah, but here, I mean, for that one, yes.
Yeah.
But here, this is a torus, so you cannot say anything from the other conjecture from this result, but other than people are wrong sometimes.
Yeah.
And these are explicit analytic solutions or just existence proofs or?
Somewhat explicit. I mean, they are. It's a power series expansion. So and there is a crank to. Yeah.
That's kind of explicit.
Yeah.
It's pretty explicit.
It's difficult to understand how he got
And
there.
do they have continuous parameters to the solution?
Yes.
Okay.
Yes.
Okay.
Yeah, and some of them, this solution is obtained by making some of those parameters sufficiently small, and then this accommodates for the whole thing to be convergent, and so that's sort of the trick.
Okay, Fabi,
Yes.
do we have example of slightly related equation where we have such a strong conclusion on the topology of the domain? To me,
Yes.
it still sounds crazy, but
No. To the Euler actually.
okay.
This is a result of mine. So I proved that with Yao Yao, Jamin Park, and Jiaxi. So you take 2D Euler in vorticity form, steady. So essentially your vorticity now sort of looks like this. And if you assume that omega is positive or non-negative, then omega has to be radial. Radial, okay, relative to a center, because everything is translation invariant, but everything has to be radial. So there is, and there is no, okay, this is a condition. But, and if you don't have that, then you can find counterexamples, so it's like really necessary. So this is a simpler equation where you have a relatively strong rigidity statement on the domain or on the level sets.
Okay. So the domain here has to be a.
Yeah, or even, let's make our life even easier. Let's take omega to be the characteristic function of some domain.
Yeah.
So now omega is 1. Then this has to be circles or annuli or collections of those.
Okay. So that's why in the previous problem, if you assume axisymmetries and you end up with this 2D thing where suddenly you have to prove that things are a circle,
Yeah.
And then so then you
Yeah, like in the section, you need to have circles.
and then you end up with something where we have examples.
Not quite, because they interact through the incompressibility. So it's not, you cannot really reduce 3D into
No,
2D.
that's reduced, but you have something related. Okay.
In some sense, yes.
So what you do here would not be a solution.
No. No. Maybe, but then it's not easy to do it for 3D. So one could expect that maybe something like, okay, so this I tried, and I didn't know how to make it work. Both in the positive and the negative direction, because you can, so there is this negative, or well, rigidity result from here, but you can also do flexibility results where you now write this as a sum of some AKs, DKs, and the AKs are not necessarily all positive. And then you can construct things that are non-radial out of this using bifurcation theory. So it is conceivable maybe that in 3D you can use this sort of bifurcation theory to maybe construct some non-toroidal domains, but so far nobody has managed to make that work because it's not as easy as in 2D. There are more conditions, and there is some magic cancellation that has to happen, and nobody knows how to make it happen. So maybe, but then I don't know how to do it.
Do these Gavrilov solutions break all the symmetries?
So what?
Do they have, does Gavrilov, this family of solutions up here, do you get rid of all the symmetries? Yeah.
No, they do, because they are supported on tori.
Well, the torus has a rotational symmetry.
Yes, so that
But the solution, does the standard solution have that symmetry?
the standard.
So you told me there must be like some simple solution.
Yeah. No, the standard solution has the rotational
But
symmetry.
do his solutions have that symmetry?
The rotational symmetry, yes.
Okay. So
Yeah.
that-
Yes.
Okay, so that's a reason why you might think that changing the shape of the torus in some way destroys the solution, because they all have the symmetry.
Right.
Okay.
Yes. But again, this is not at all clear whether the answer may be yes or no. Like
No, but if you told me that they didn't have the symmetry, then I would have very much
right.
said,
Then the answer is no. Yeah.
Yeah.
Right.
Okay.
So that's maybe another
Okay, yeah.
possibility.
Yeah, this is something we could throw sink our teeth into.
Then maybe can you write like 2 grad?
Okay, so these are nice. Whenever theorists want to defend our honor for us a problem, should we talk about some totally different class of problems? Or,
I have maybe one more in a completely different class. So this is more, and here I essentially don't know theory, but I can explain what it is reduced. So this is more on the interval arithmetic computer assisted proof realm. So this is more towards computer assisted proof. And in connection with singular integrals. Okay, so this is a problem in minimal surfaces in which I claim that I know nothing. But let me reduce it to an integral. So suppose that I have some domain on Rn, and we call sigma, the boundary of the domain, and in S is going to be some number between 0 and 1. So I'm going to define an S minimal surface to be the corresponding E's and sigmas that satisfy the following equation. Okay, so this is an S minimal surface, and then there is a paper by Davila, Elpino, and Wei in GEMS a few years ago, where they proved stability for very small s. And dimensions, and I will be more specific as what do I mean by stability. Stability of a certain surface for some dimensions equal to 7, and this is the stability of this thing. The cone that is indexed by 2 parameters, n and m. Alpha is a number, and this is called the Lawson cone.
What was the numerator of the HS?
Yes, sigma.
And the under the integral, what's the numerator?
Oh, the characteristic function of the set E minus the characteristic function of the complement of the set E.
Ah, okay.
So this is the statement, and the statement is perturbative in nature. They can analyze the cases is equal to 0, and then they prove some kind of continuity in terms of S. And then so the proof depends on some horrible number, singularity. Involving elliptic functions. And then the question is to give the full picture for all n, m, and x. Okay, and this is more kind of an implementation sort of problem as to develop or enlarge some functions or some libraries that can deal with singular integrals. So one could think of this as being a concrete task and like develop some nice fast integrator that can do singular integrals, or maybe more concrete that says, okay, something that can solve this problem. Okay,
Why does it get harder as it's larger?
Because it's not perturbative anymore. Like the way they can, the problem is that this thing is difficult to understand in general. So they can only understand it for S is equal to 0. And then
they perturb slightly right.
Exactly. Then the results, I mean, they can always do numerics and so on. And they see that, oh, there is some curve for certain S, like that depends on N and M, where there is some threshold of stability, but they cannot really prove anything. So this is really about turning some numerics into a proof. Like the numerics are already done, or somewhat done in the paper. They have a table with many values for N, M, and X, and an explicit expression of the thing that really matters. Now this is more of a question of like usually the second part of these projects that turn a numerical statement into a proof. In this case, by means of doing some rigorous computation, like some rigorous integration.
But it is elliptical. Where's the ellipticity coming from?
The ellipticity of
so why does the solution involve elliptic function?
Because I can tell you how this functional. I mean, there is some functional that for a given cone of parameters n, m, and a given problem indexed by s, they can reduce it to two quantities, and if one is bigger than the other, the cone is stable, and if it is smaller, then it is not. So that's where the elliptic functions come into place in this reduction into this kind of nasty integral. Okay, so the integral is horrible, but it's too big. So it's not so horrible, maybe.
I'm sorry, what do you mean in this context?
I think my understand again, I'm not an expert here, but my understanding here is that if you perturb the cone a little bit, then you're going to still get a minimal surface around.
So it's a family.
Yeah. But don't quote me on that.
That's
Is this recording?
Oh shit. Yeah, this is kind of what I had in mind, but of course, you know, anyone can propose or suggest.
Yeah, okay, very good. This is a kind of a wide range of.
Yeah, I mean, another idea is for maybe to do some kind of comparison between PDE, so ML methods for PDE. I mean, now there are many methods out there, and it's unclear which one is better, whatever that means.
Oh, yeah,
So
that's a very important, interesting question. I mean,
Right.
again, for a discussion like this, it's more like kind of setting out the problem, properly. I mean,
Right.
That's,
Right.
that would certainly be if people want to have that kind of a discussion. So we have scheduled, 3 more meetings, but of course we can schedule more meetings. We can have informal discussions. So that's another possibility, that kind of not totally open-ended, but broad discussion around it. Yeah, okay.
So I'd like to propose a different I don't know.
What was this one called?
Lawson cone.
I'm not gonna-
LAW.
Why, we actually know
Yes,
the
sir.
Lawson code from our
Oh.
string theory, so.
Oh, okay.
So we wouldn't get called the problem that because we would just be going in some sort of different direction. Okay, so, okay, minimal, some sort of S minimal surface.
Right.
So I'd like to propose a problem that sort of connects PD with sort of like a very different type of problem. It connects sort of PD with graph theory combinatorics, basically. So so there's sort of two kind of problems. Like the problem I'm most familiar with, if you take the non-Schrodinger equation. And you're looking at, you take it on the Schrodinger equation and you take its Fourier series. Okay. And you consider random initial data. And I should say this is on the torus. On H3, or let's say TPL, so of length L.
So what's the length?
Just a torus. I mean, you can always scale out L, but it's useful to. So the torus is just left L, and then you take L to infinity, and then amplitude to 0. This is not actually true, but you don't have to. So that was the discussion. I said this is true, and then you end up with an effective equation. Equation on AK on R3. So you could think of like the AK is on a lattice. So the Fourier series is on a lattice, and then as you take L to infinity, you can think of this the grid spacing to be like 1 on L, and so the lattice goes to R3, and you end up with this effective equation. I mean, physicists do this like very informally, okay? And then you end up with an equation, and then
the question is to justify this rigorously. And this has been proven. So we have a case of, and I should say an analogous problem is where you take the n-body problem, where you have these hard spheres, you take n spheres, hard spheres, and you consider you take these balls to 0 and you take a number of spheres to infinity, and you end up with the Boltzmann equation. So this is Hilbert's 6 problem. So these two problems are actually, they're very different, but actually quite related. So how does this end up in the combinatorial graph problem? So how do you actually prove this? So you know what the effective equation is, and you know what the dynamical equation is, and you want to connect the two. So one way to do this is you take a dynamical equation for this, and you do Hamel expansion. So you do Hamel expand infinite number of times, and then you do the same thing on the effective equation at the end. And somehow the terms you get on one side and the terms you get on the other side have to match, and they do match. And you can draw these two Hamel expansions as Feynman diagrams. Now, the only thing is that the dynamical equation have many more graphs, have many more Feynman diagrams, which don't appear in the effective equation. But somehow they have some sort of degeneracy, which you can observe, and they all sort of cancel out as you take L to infinity. And
that's true of the random initial data is the problem.
So it's absolutely essential for the cancellation. So you basically, it limits the number of interactions that can actually occur. So if you think about like if you think about the Boltzmann equation, you have all these spheres, right? I mean, you could have crazy configurations, right, where all the spheres are perfectly lined up, or whatever, and obviously you're not going to get anything useful.
When you say random, do you mean a distribution, or do you mean except for the next set of measures?
So in this case, it's just so they're Gaussian. So what the initial data is set to be.
So it's drawn from a normal distribution.
Yeah, exactly. So you have some deterministic amplitude, but then it's multiplied by some Gaussians.
This is a Gaussian, right?
Yeah.
But then so are we trying to get expectation values?
Yes. So I should say you only get this effective equation in expectation.
Okay, good.
Yeah. So of course, you have to get it in expectation. Yes.
Okay.
And so what you see, and the nice thing about this, so this is actually a generic problem in like physics, this kind of thing that you could apply it for in many things. But what I would like to see is I know the answer to this problem. I know what the combinatorics are. And so I would like to see how to rediscover it using machine learning. So basically, what this kind of reduces to is you have these trees which come out from two Hamel expansions, and if you consider cubic MLS, there's always 3 branches. And you can think of, and then you're considering, say, the amplitudes. So let's consider 2 trees, and I mean, I'll go, if people are interested in this problem, I'll go into more details of what all these trees are. And when you take an expectation, you end up having to pair these trees in some way. You have to pair these trees in some way. Okay. And when you draw such a pairing, this corresponds to in this case, it will be
1, 2, yeah, 1, 2, 3, 4. So 4 linear equations. And 4 quadratic equations. And the question is if there's some degeneracy in these equations. So are some of these quadratic equations kind of linearly, do they have like a full rank or not? The maximum rank they can possibly have. So you can actually write this down as a matrix. You can take these pairings and write this down in the matrix, and then you can compute its rank. And the question is like, so the first thing I've actually written code.
Sorry, what are these equations then?
Sorry?
What are these equations?
So these are very simple equations. So like these are like if I call this K1, K2, K3, K4, which are the wave vectors that corresponding to the, and then K finite.
So constraints on the K's?
Yeah. So the linear equations are very simple. So it'll just be K2 minus K3 plus K4 equals K1. And each time there's a branch, there's a linear equation like this. And the quadratic equations, it's similar, except it has more to do with, it's not quite equal. This has to do, these ones come from the phase. So it comes to do with whether they're resonant or not. So these have got to do with resonances. And this is actually not equals, this is minus K1. And then is of a certain size. So this is not actually an actual equation. But anyway, you can think of it as in terms of its degeneracy. Let's just say these are just, let's say it's not the equations, they're quadratic expressions. Or quadratic polynomials. Okay. And so the point is like how do you show, how do you show that these what you see is that you have these like Duhamel expansions on one side, Duhamel expansions on the other, or groups of graphs on one side, and all the ones that don't match have some form of degeneracy. Like you end up, you can show that these quadratic polynomials, once you plug in all the linear things, one of them is linearly dependent. And so one thing I could, and this, you could imagine such problems arise in 1,000 different things.
So there is some sort of more graph theoretical combinatorial conjecture implicit in what you're saying.
Yeah, and how you prove it is you have to show, you have to organize the graphs in a certain way, and then you have to show certain structures at the end. So I can go into this. It has to do with like how many edges there are and things like that. But the question is like, and as I said, for this particular problem, it has been proven, and they found these structures. But the question is, like, as I said, there's many problems like this, but just the fixed idea is it would be good to work on a problem that we know the answer to, and whether we could use ML to discover these structures. And so it's a very concrete problem. I already have code that generates these graphs randomly, and then one question is just, can you predict the rank? Like I have this graph, it produces a matrix, it can produce the rank. Now can you create some sort of neural network that without actually doing the full computation predict the rank? And then the next question is like, how can you say you had such a neural network, how can you sort of look at it and infer from it some sort of what structures is this neural network looking for in determining the rank.
How big is the computation if you were to do the full computation?
I mean, sorry.
So you say you want to neural network to predict the thing without doing the full computation, but how big is the full computation?
I mean, so you can do this for any, it can be as big as it possibly, as, you can do this for, the problem is for, you can do this same computation for any length n trees, and n can go to infinity.
Okay.
So for the, so that's the problem, is that you can't do it for, because the computation is small. For n is small, you can do it all directly.
So in M, you need like a recurrent neural network or something like that to handle the infinity.
Yeah, so I mean, the whole point is to see if you can get it to take n finite, and see if you can discover something from n equals is finite. See if you can discover the structures. See if you can just discover the structures n finite, and then you go ahead and prove it by, as a mathematician, go ahead and prove it.
And to prove that you've discovered something n finite, you train with a certain n, and
Yes.
you evaluate with a larger n.
Yes, for example, yeah. So you can always test it, but you don't have to, because there's so many. The number of graph combinations grows factorial. So if n is
not
even sufficiently large, you can just do it with random graphs for a specific n, because there's so many combinations. So you don't have to go to the next n to.
You might conjecture some structure, then get evidence for the structure.
Yeah. And as I said, I know the answer for this one. So I actually know what but it's these 100 and these papers are it's several 160-page papers to prove this. And it's a very big result, and that you could see these sort of problems in all sorts of crystals and all sorts of there's 1,000 different versions of this. I mean, it's this basic idea of you take some dynamic equation, and then eventually you introduce some sort of randomness, and then you end up with an effective equation, and you want to match the two. And this is what is done in physics all the time informally, and the point is to do this rigorously. This is a Hilbert-6 problem.
So roughly, so when you say you know the answer, you mean you know what, if I was writing down two graphs and how they are paired, you would be able to tell me this as rank n minus 1, n minus 2, n minus 3, whatever.
At least I can give a bound, yeah. So it has to do with the number of, it has to do, you can actually just take this and turn this into a graph. It's a different graph. And then it has to do with how many times there's 3 edges. So I mean, there's specific things. But it becomes actually, I don't think you can quite say exactly. And if you could find, in the proof, it's more like you can find bounds. If you find certain structures, then you can reduce the dimension. But you can't, there's not a statement that says that you go from this. What I really like is exactly what you said. So you have these topological structures of the graph. What is this rank? And that you don't actually have. Exactly. So it would be nice if you had a more precise version of that.
Do you have any idea of architecture you use for that? If n is finite, you could flatten all the thing and put 0 or 1 depending on if you have connections or something like that.
This is.
Well, it probably should be really turned into a purely graph theoretic.
Yeah, it will be a purely graph theoretic problem.
Once we see it just laid out like that, we'll have a better sense.
And I have code that will randomly produce these graphs and tell you the answer, tell you the rank. So I can share you the code, and then you can try to create go ahead and try to create a neural network that does it without using the code, that predicts it without actually.
I know for this for smaller structure, but still for graph, François Chaton had trained the transformer to try to predict quantities of graph, and there were some basic findings about when you train some distribution are better than others to generalize that sort of distribution, so to train quickly. I'm just saying this because it comes to mind when I say this.
Adam, do you have
I think I have something to ask.
I need to understand the problem a bit better.
Right, yeah, I think we're just, I think.
But I can turn this problem to a completely graph problem. You don't have to know anything about these.
Well, I mean, if we're interested in that, then we can set a some practice to do that. Okay, so we have 15 more minutes now. We maybe have time for somebody else to outline. If we want to follow this approach of dividing up into groups to each group will focus on a problem, we should probably start discussing that. So that works well in other weeks. This is a pretty broad range, a lot of interesting stuff here. Does anybody have like one more problem that we just really can?
Kind of, I should have prepared something. I haven't really thought about it so much, but effectively I thought, something about, I'm sure there are lots of like different open problems in the field of minimal surfaces or calibrated geometry, like they're sort of adjacent in some way. And if you could try and use ML tools, PD tools in some way to try and identify or analyze new examples of calibrated submanifolds or even just minimal surfaces, like a simple example, 2D or 3D. That might be quite fun.
That's some sort of nice numerical problem in minimal surfaces. I'm sure there's quite a lot. I mean, do any of us here know, or do you want to?
I mean, even just identifying calibrated submanifolds, I don't think this has been done in the context of anything to do with machine learning. That might be correct.
Okay. So just maybe find new ones. So, I mean, some of them, like holomorphic, that
yeah,
right.
Right.
A problem with, but
special Lagrange
special Lagrange. Maybe that's a problem. We could at least, again, I think the problem is we're not totally sure what's known. Is there some like outstanding challenge in this? So I mean, this is actually where this law of Cohen actually comes up in our field. Do you know what a calibrated submanifold is?
I've heard the word.
Yeah, I mean.
Okay, so let's see if I can get this right. Okay, so this says that particular type of minimal surface, there's this idea of a, it could be in a metric space of some given velocity, but just an Rn. There are these, so K form omega is a calibration. If, what is it? It's like it's a K form. So if you restrict it to some K plane, so I don't know, VK, then so this is a K form, and so at every point in VK, this gives you a number. You can think of it as of course you could take a domain within the VK and integrate it and get a number, and then the claim is that this is always a lower bound for the volume. Okay, so we restrict the volume form to this VK. Does that make sense?
Yeah.
Yeah. And so now you can find things where what is it? It's so that's the definition. So now we're going to use this by
Omega typically needs to be closed as well.
yes. Okay. So now a calibrated submanifold is going to be one where we saturate this at every point, and then this. Let's see. So I'm missing the ingredient of often when you apply this, there's a different, related thing that you're setting to 0. So what's the
the other, I mean, this is the, yeah, when that's saturated, that's a calibrated manifold. I think the point is that in the context of special harmony manifolds, you often end up with large clusters of
Yeah, but why is it easier to find these guys?
when you have a special harmony.
Yeah.
In some sense, it's because, well, you will automatically have a closed form, which is in fact covariant constant. And that form is invariant under the action of some symmetry group of your special harmony. So in some sense, it means that you should expect the class of calibrated sum-animals to be sufficiently large that it's interesting and you can actually find them. You don't have to have special harmony to have these guys, but
But there's also a test which doesn't involve the line.
Oh, right, yes. So something needs to restrict to 0.
Yeah, so what's the thing that needs to?
Well, for SU3 on manifolds, it's the real part of the imaginary.
Let's just do special Lagrange, because that's the case we were being used as a pattern effort. Okay, so now this is in R2 so that's even. And now there are these preferred forms, okay? So it's easiest to think of this actually in terms of the complex. I could write it in some other way, but so. Okay, and then okay, so now there's this preferred half-dimensional M form and this preferred 2 form. Okay, and those are the calibrations. Of course, there's many more things you could talk about on our end, but these are ones that actually also exist on curved manifolds of SU-Lonely. So we're particularly interested in those, but they make, they satisfy these conditions already. The problem's already interesting on R2. And so now the special Lagrangian. So Lagrangian would be, okay, so I called it, well, let's say sigma. Okay, so sigma is a m-dimensional submanifold. And then if I restrict this 2 form to sigma, that's 0. So that's the definite. So you can think of this as defining a symplectic structure of the manifold, and that would be the definition just of a Lagrangian manifold. And so there's lots of those, and locally those are determined by a function, and you have to kind of horizontal word construction. Again, then a special Lagrangian is there's the restriction of, let's say, the imaginary part of this second form big domain is 0. And I should generalize a little bit and say that I have this one real parameter family of these guys where I multiply by a phase. So I choose one of those and I say that the imaginary part of this omega theta restricted to the manifold is 0, and that's the special condition. And then that informs exactly that it's calibrated, saturated this inequality. So that's a way of getting minimal surfaces now. And also a lot of other actually is an example of this also in the appropriate dimension and the right choices. And then there's a deformation of that, which is like, I forget Harvey and Mahler, that kind of blows up this, or blows it at the origin in that original cut. And then quite a bit of work goes done on these things. And so the broad question, of course, is to find an interesting problem here that we can study in a minute.
So one thing I would say is that, like in general, I was good at finding mechanics, but one thing you'd want to do in any of these kind of problems is to reduce the dimension, because you'd have to have some ansatz to reduce your very dimension setting.
Well, yes and no. I mean, we do a lot of stuff in 6 or 3 complex dimensions. And the thing that maybe the thing that saves us is that everything is very smooth and analytic, generally the solutions that we're looking for. And so like these Calabi metric, which we could get into on a 6 real dimensional manifold. That's 6 dimensional, where we get pretty good results. But I mean, it's you kind of have to get up to 6 for this particular problem to become something new, because if you're in 4, then there's this more complicated story. It's called hypercalar, and you can turn it back into like this holomorphic and some other complex structure. And,
But I'm just saying, like, how would you approach something numerically?
How would we? Well, okay. I mean, so the basic thing here is that locally, one of these manifolds is defined by a single function. You say that you split into D's and Q's, and you have DL by DQ. And so then, in terms of that single function, this is a Mondrian equation, this condition. And so that's what we're trying to, concretely solve. And so that would locally be a 3-dimensional equation if we just grant that the solution, is, in some sense, the manifold's divided over this 3-dimensional base, and we're just, putting, so at least we've gotten it down to 3 from 6. So okay, so that's indeed that's closely related to our RBL thing. So we even have code that does this in some cases. And now what's a open problem that we could study within this domain?
Yeah, I mean, I think Kit has in mind learning to sample submanifolds such that the Monte Carlo estimates give rise to allow you to compute the volume submanifold that way, right? You're imagining it as a sampling problem with fixed background metric.
Fixed background metric, probably, yeah. And then maybe, I mean, you can define in principle using some kind of network and embedding into that manifold.
Well, now we have to get now we can't just talk about R2. Right now we really have to get into the metric aspect of the.
Yes.
And we're getting towards. I mean, why don't we?
May I make one comment? I think there's a slight broadening of the problem that's important to state is important. These calibrated geometries are very beautiful and important in string theory, but for comparison to real-world physics, we also know that we need minimal cases where there simply is no calibrated representative. These are always, when they exist, they're always volume minimizing in homology, but there are certain cases that we really care about where there are submanifolds where there simply are no calibrated representatives within that homology class.
Well, and that's I actually do know questions like that, where it's like if you could find this is a lot more minimal manifolds than you would think are of this type, and if you could find one that is not of this type, is actually kind of interesting.
I guess any 2-cycle and a G2 manifold is not of this type.
Yeah.
But there's this rich class. I mean, I think there's both, and in some sense, this problem is the stepping stone to the general problem, which is just the minimizer.
Yeah.
Yeah.
But okay. I mean, this is another kind of. This connects to all sorts of things, and we have a number of experts on it. Okay, what do people think of? We have 5 kind of interesting, all interesting problems, and so one way to proceed is to divide up into groups, and each group focuses on one of these problems, and then we'll meet in subgroups, and they'll come back to talk about our progress. Does that make sense? Or?
I was thinking also, like, maybe it would be good, I don't know how many people have exposure to, like I think it would be good if Harvey could give a talk about, like, interval arithmetic, which is something that I don't think many people here would be exposed to, but they might be,
I think that would be great.
That might be interested.
Sure. Okay, excellent. Okay, so that's another thing.
A separate thing.
Yeah, exactly. So we could schedule that, we could do it Wednesday during the already scheduled session. So we could start off on Wednesday by, again, each reporting our progress. We can also meet again tomorrow if you want, but we could, in any case, start off on Wednesday with that, and we can have a talk about methods. That would be great. Okay, good. Are there other proposals for like talks that we might want to solicit, or somebody might offer to give? I mean, you don't need to answer right this minute. You can propose it also on via Zoom. Everybody should be on via Zoom if you're not already. Okay, so now the way that this protocol that is used at the AIM, the American Institute of Mathematics, and your group used this very effectively, where you first kind of vote on each of the prompts just to establish the level of interest. And then once we do that, then we go in increasing order of number of interested people and volunteer to the various groups. And then that's it. So in this first phase, you can vote for any number of the prompts. Just, what are the problems that you think, how would you prioritize in terms of what we as a group worked on? Do you think that's a good problem? I guess there's this Lamacine vortex. Okay, I like that. What's that problem?
I like the problem.
Raise your hand. There, 1, 2, 3, 4, 5, 6, 7, 8. Okay, there's the Gadd's conjecture. Who likes that problem? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay, there's the
Predict 8 for the rest.
Okay, then there's the S minimal surface problem. Right. 1. Okay, good.
What was it again?
Oh, this is the one.
The one with the integrals.
This is kind of singular integral defining. Yeah. Okay. Okay. Then there's this kind of graph structure related to denominator Schrodinger and random fields and that kind of stuff. Who would like to discuss that? Okay, hang on. Put in. This 4, 5. Good. And then this whole topic of calibrated geometry, Calabi geometry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, great. Okay, so that's our first phase. Drew, are you there? Do you want to put in your vote or?
Yeah, I don't feel like I'm knowledgeable enough to
Okay.
render a meaningful vote.
Okay, that's okay. Okay, so then.
You can cross 3 maybe.
Yeah, well, somebody can still volunteer and then move around, but you're okay to cross out 3, okay. Okay, so we'll cross out 3. Okay, so then that
And
gets
just
us-
write the paper on your own.
Okay, so then this graph structure problem, who wants to join that group?
I'd like to understand the problem more formally. I think I still don't have a
That's
crystal
right. It's
statement.
not, that's right. You're not bound to this, like we could have one meeting.
Maybe people can float around and go in between.
Yeah, that's right. Okay, so maybe who would be interested in just having like one meeting to kind of get that problem more spelled out and get a sense about it?
Yes.
Okay, 2. I'm interested at that level 4. Okay, so meeting. Okay, so maybe okay. Well, I think for each this is the point where this protocol they were typing stuff and it was getting complicated. So for each of these things, maybe somebody can. Well, I mean, one way we could do it is to take a picture of who's raising their hand. Maybe we'll just set up a message. We'll set up a Zoom.
Yeah, we can put posts on Zoom.
Zoom topics for each. Well, let's have Zoom topics for each one, and then people can just add, put a comment there, so they can like a message, and we'll assign. We'll assign it. And then if you join this group, you can join another group because unless as things stand, the proposal is just to have a meeting to explore that problem further. Okay, then the Lamacine vortex, who would like to join that group?
So are you just asking us to raise our hands?
Yeah, raise your hand.
I raised my hand.
Okay, good.
But this is the second time around, right?
Yeah, this is the second
Now you're
time around.
subscribing.
So I don't know what's the difference. I'm writing down people's names, but as I'm lazy, I'm going to just put the names of these problems under the appropriate channel, and then you can like say yes, at that point. So there are people, but I still want to, so everybody else knows at this point, just raise your hand if you're interested in really putting some serious work into this problem.
Discussing.
Serious at the level of what you're doing in a week. So it just means somebody maybe should try to cut up some kind of simple numerical thing, and then we'll see how it all works.
I mean, for this, I would just sort of try to sit this working code of 5 steps.
Exactly, okay, I mean, that was a stability thing, so, just see if that blows up. Okay, so there's.
But there is no big commitment in the sense
Right,
that
that's
people
right.
can start on one and then.
That's right,
another
everybody can switch, but something where you do plan to meet and engage. So again, this one, let's go to number 2, I'll raise my hand for that one. Okay, so several people are interested in that, that's good, so we'll put that down. Okay, let's come back to 1, land Machine vortex. Raise your hand if, good. Maybe the step of writing that I'll make.
We're just gonna organize meetings by.
Okay, and then the calibrated geometry, we want to discuss that. Okay.
Are the meetings going to be overlapping?
Yes, that's the idea,
Oh,
is that in general.
So I voted for 3, actually.
And they can each organize without necessarily, but then we report on what we're talking about in our progress. And as things stand, the next scheduled meeting would be Wednesday morning. Oh, no, sorry, Tuesday afternoon. So Tuesday afternoon will be a scheduled meeting after 2. Okay, so I think that's good for today.
So how we set up this initial meetings? Is just on the server?
Yeah, that's right. We did discuss.
So I'd say we do the 5 steps, and each people propose it, can maybe